This video is about Kuhn and his views about the relationship between successive paradigms. I want to focus, as Kuhn does, on the relationship between the Newtonian paradigm and the Einsteinian paradigm. In the structure of scientific revolutions, Kuhn is interested in arguing against a commonly held view that Newtonian physics is just a special case or a limiting case of Newtonian physics. And he attributes this view to the logical positivists and argues that they must be wrong, although he recognizes that his view is in the minority. So the question before us is this: is it the case that if I start with Einsteinian dynamics, I can derive Newtonian dynamics? And as Kuhn explains, and one hears even contemporary physics say, the answer to this is usually thought to be yes. It's a very simple mathematical procedure that takes you from the equations of Einsteinian dynamics to the equations of Newtonian dynamics. And the mathematical procedure is the procedure of taking a limit. And you basically start with the equations in Einsteinian physics, and you take the limit, and you can write this down in several different ways, but you can take the limit for quantities for which v over c squared is much less than 1. And if you perform that mathematical operation on those equations called taking the limit, which you might have learned about in calculus, then what you end up with seems to be the equations of Newtonian dynamics. And that's what Kuhn believes is a sort of standard, commonly held view, that if we start with a bunch of equations in Einsteinian physics, we can derive another set of equations, which are equations in Newtonian physics. And so it seems as if Newtonian physics is just a limiting case or a special case of Einsteinian physics, and this would mean that the two paradigms are entirely consistent and compatible with one another. Kuhn is trying to argue against this view. So let's suppose we start in Einsteinian dynamics, and all we want to look at is the quantity that we call relativistic momentum, or the physicists call relativistic momentum. The important thing here for us to notice is that there is this factor in the bottom of this fraction that is 1 minus v squared over c squared inside a square root. And what we notice about this quantity is that if the v over c is very small, then its square is going to be very small compared to 1, and this bottom quantity here is going to basically become 1. So if I take the limit for velocities for which v over c squared is much less than 1, then what I end up with is p equals mv. Now, as it happens, this is the same sequence of symbols we would be writing down if we wanted to write down the expression for momentum in Newtonian physics. So why isn't this an example of deriving a Newtonian quantity from its corresponding Einsteinian cousin through this process of taking the limit? Why doesn't this show that we can derive Newtonian physics from Einsteinian physics, and that therefore the two paradigms are continuous and consistent with one another and compatible with one another? Well, Kuhn has this very interesting sentence in the Structure of Scientific Revolutions, where he says this. He says, look, it looks as if what we've done is arrived at the Newtonian law. However, he says, and I'm going to copy it down here because this is going to be an important thing for us to discuss. So the physical referents of these Einsteinian concepts are by no means identical with those of the Newtonian concepts that bear the same name. This is a hugely important point that emphasizes the distinction between language and world, and emphasizes everything Kuhn has to say about the incommensurability of meaning across paradigm shifts. What exactly do each of these terms refer to in the real world? Kuhn focuses on this term right here, m, which we usually say is mass. And what he's telling us in this quotation is that what this term mass refers to in this equation, which I've derived from the Einsteinian one by taking the limit, what it refers to is different from what the same m refers to if I were to write down the Newtonian expression. So let me try to illustrate that really quick. Okay, so in the Einsteinian case, if I take the limit, I get P equals mv. In the Newtonian case, I don't have to take the limit, it's just the definition of momentum. And it looks like they're the same, right? Except that this m that I've just circled here, what that refers to is different from what this m in this equation refers to. Because the m on the Newtonian side refers to a quantity that combines using the principles of simple addition. So that if I have two masses that are coming together, say two balls of putty, and collide to create one big mass, if each one of these is of mass m, the resulting blob that has the two of them put together is going to be of mass 2m. But on this side, on the side of relativistic physics, that's not true. If I have two masses, each one of mass m, that collide to create some bigger blob, the result is not exactly 2m. It's going to be 2m minus some amount of energy released in the interaction divided by c squared. That's because there's a sense in which mass and energy are equivalent in special relativity, which is not true in Newtonian physics. And that's why, for Kuhn, even though we can derive an equation that looks the same because it has the same symbols in the same order, it does not follow that what we have derived is Newton's physics.